Hey guys, Professor Calculus is here. Today in this video we're gonna see how we should solve this integral here. But before, make sure to like and subscribe as it is free and you can always change your mind later. So we can solve this integral with contour integration and complex analysis, which is a little bit harder. Um, but there is another way that we can solve this integral, and that is the Feynman's trick, Feynman's technique of integration, aka differentiation under the integral sign. For that, I'm gonna be needing to introduce a new parameter, cosine xt over 1 plus x squared dx, and if I find I of 1, that means I have found cosine x over 1 plus x squared dx. Now, to solve this integral, first I'm going to take the derivative of both sides with respect to t. This term is going to be I prime of t. And keep in mind that we're taking the derivative with respect to t. We're taking derivative of an integral here, the cosine of xt over 1 plus x squared dx. According to Leibniz rule of integration, this is gonna go inside, and the I prime of t is gonna be becoming a partial derivative, partial t of cosine of xt over 1 plus x squared dx. And when we're taking a partial derivative with respect to t, we consider these constants, the x is constant, and just we take the derivative of the terms that have a t term in themselves. Sorry guys, my chair is making lots of sound today. I don't know if you can hear it or not, but okay. So this is gonna be negative x sine of xt over 1 plus x squared dx. And the trick that I'm going to use here is multiply and divide by x once, and after that I'm going to add and subtract a sine of xt, which you'll see later why. Negative x squared sine of xt plus sine of xt plus minus sine of xt over x times 1 plus x squared dx. And I can pair these two up together. My I prime of t is going to be negative x squared sine of xt minus sine of xt over x squared x times 1 plus x squared dx plus the negative infinity to infinity of sine of xt over x times 1 plus x squared dx. Now, I can factor out the negative here, and then you can factor out the x squared, the sine x, sine xt times x squared plus 1 over x times 1 plus x squared dx. These two here are gonna go away, and I'm left with the integral from negative infinity to infinity of sine of xt over x dx plus the integral from negative infinity to infinity of sine of xt over x times 1 plus x squared dx. So first I'm gonna work on this integral here, the integral of from negative infinity to infinity of sine of xt over x dx. What is that? Well, For that, I'm going to let u be equal to xt. Therefore, du is dxt, and dx is dut to the negative 1. X equals ut to the negative 1. And if I do the replacement here, is sine of u over ut to the negative 1 times dx, sorry, du, t to the negative 1, and these t to the negative 1s cancel out, which means that my integral as a whole is the same as sine u over u du. And actually this integral has an exact value, which I derived in my other video, and its value is pi. Thus, you can go and see that video if you feel confused about this integral right here. It's very long proof. I'm not gonna prove it all here because it takes a lot of time. Thus, my integral is gonna be negative pi plus the integral from negative infinity to infinity of, what do we have here, sine of xt over x times 1 plus x squared dx. Now, right now, I'm gonna take the derivative of this thing once more, and again I'm gonna have to take the derivative partially, and I'm gonna get x times cosine of xt over x times 1 plus x squared dx. These two x's are gonna cancel out, and my I prime prime of t is negative infinity to infinity of cosine of xt over 1 plus x squared dx. Now, how do you see the pattern here? First of all, do you see the pattern? This is actually our I of t here. So this thing right here is I of t, and thus I can say my I prime prime of t equals I of t, and I prime prime of t minus I of t equals 0, and this forms a differential equation that I need to solve it. And I can write it as first of all I need to find the roots of this differential equation. So according to the roots of differential equations, I'm gonna have r, this is the root of my differential equation, r squared, the order of this the derivative, minus 1 equals 0, because if it had if it was first order derivative, first derivative of t, I would have written here minus r equals 0, but because this is 0th order of derivative, I'm gonna be having 1 equals 0, and therefore the root is plus or minus 1. Be careful, this is really important. Our roots are plus or minus 1. So I can therefore the general solution to a differential equation, I'm gonna write it here, y of t is c1, first constant, e to the negative e to the r1 plus c1 e to the r2, and in this case here, our I of t, c1, or our r1 is 1, thus I'm gonna write, it should have been a t here, so it's gonna be t plus c1 e to the negative t, the second root of my differential equation. And I can express the I of t that we saw here, this one, in this form as well. Therefore I can say the integral from negative infinity to infinity of cosine of xt over 1 plus x squared dx is c naught e to the t plus c1 e to the negative t. So now our problem is that we have to find these constant of integrations, the C1 and C2. How do we do that? First of all, I'm gonna take the limit as t approaches 0, or I can also say as if t equals 0, what happens? If I let t be equal to 0, I'm gonna get the integral from negative infinity to infinity of cosine of 0, 1 plus x squared dx equals c naught times e to the 0 plus c1 e to the 0, which these zeros are gonna, e to the zeros are gonna be 1, and cosine of 0 is 1, and I'm gonna have the integral from negative infinity to infinity of 1 over 1 plus x squared dx equals c naught plus c1. And how do we find this integral here? If you look really closely, you're gonna see that this is the derivative of arctan function. Thus this integral is arctan of x, the limit from negative infinity to infinity, equals c naught plus c1. This limit, arctan of x, negative infinity to infinity, infinity is not a number but rather a concept. And if I want to find this limit, I have to find the limit as x approaches infinity of arctan of x minus the limit as x approaches negative infinity of arctan of x. This is the improper integral. Now, some of you might not know the graph of the arctan integral arctan function, but we're gonna try to write it here. This thing right here is the graph of arctan of x, and here this asymptote here, I'm gonna write it in red. This asymptote here and these asymptotes here, these are pi over 2, and this one is negative pi over 2. Thus, as my x approaches infinity, as the limit as x approaches infinity of arctan of x is infinity is pi over 2, and the limit as x approaches negative infinity of arctan of x is negative pi over 2. Thus, this limit here is pi over 2 minus negative pi over 2, which is pi over 2 plus pi over 2, which is 2 pi over 2, which is pi. So, thus I can say c naught plus c1 is pi. So have this equation, call this equation 1. c1 plus c naught equals to pi, the equation 1. I'm gonna put this right here, and I'm gonna be wanting to find another equation to solve this system of equations. Notice that I prime of t, and first remember the I of t, which is c naught e to the t plus c1 e to the negative t. And if I take the derivative of it, it's going to be c naught e to the t minus c1 e to the negative t. So remember that I prime of t was negative pi plus the integral from negative infinity to infinity of cosine of xt, sine of xt over x times 1 plus x squared dx. And I'm going to equate these two to each other. C naught e to the t minus c1 e to the negative t equals negative pi plus negative infinity to infinity of sine of xt over x times 1 plus x squared dx. We can use the same trick that we used there, and that is the letting the t be equal to 0. And, for that, these two are going to go away. I'm going to have c0 minus c1 equal to negative pi plus the integral from negative infinity to infinity sine of 0 is 0. And the definite integral of 0 is always 0. So I'm not going to write this integral here. Thus we can conclude that c0 minus c1 is pi, which means that c1 minus c0 is pi. Sorry, negative pi here, I meant to say. So I'm going to write this here. c0 minus c1, c1 minus c0 is pi. And if I add these two equations together, I'm going to call this first of all equation 2. And if I add 1 plus 2, I'm going to be getting these c0s are going to annihilate, and I'm going to have 2c1 equals to 2 pi, which means that c1 equals to pi. And if I plug it into here, c1 equals to pi. I'm going to use the equation 2 here. Pi minus c0 equals to pi. These two are going to go away, and I can say that c0 equals 0. Thus we have found our constant of integrations, and I can say safely that c0 equals 0. Since c0 equals 0, I'm going to say 0 e to the t plus c1 is pi e to the negative t. This is going to obviously go down to 0, and I of t is pi e to the negative t. Hold on, we're almost there. And we said that the integral from 0 to infinity of cosine xt over 1 plus x squared dx is pi e to the negative t, and our goal was to find I of 1, which was finding which led us to cosine x over 1 plus x squared, our initial integral, which if I plug in 1 for t in here, I'm going to get pi into the negative 1, which means my integral is pi over p, pi over e, sorry. Therefore, write it here, my integral from negative infinity to infinity of cosine x over 1 plus x squared dx is pi over e. And that was one hell of a work that we did here, but hopefully you did understand it. If not, please ask me questions in the comments. Hope you enjoyed this video. Please like and subscribe and share my videos, and I'll see you next video.